All right, so we did these notes to start with, and now I want to go back and I want to look at example, or not example, it was the warm-up question number 4, but I didn't want you guys to get frustrated looking at it, so we're going to look at it together. This isn't a problem that you necessarily you might have figured out how to do on your own, but it kind of has a little trick to it that I think would make it hard to figure out on your own. So this problem looks different from the other ones because it's not set up to look like the sum of an infinite geometric series. It's an ln. It looks kind of weird. So what I'm actually going to do is I'm going to take the derivative of this, and the reason that I'm going to do that is because when I take the derivative, it turns it into a rational function. So the derivative of ln, if you guys remember, is 1 over the inside of the parentheses, and then we have to do the chain rule, so we have to multiply by the derivative of the inside of the parentheses, which is -1. So that means that f prime of x is -1 over 1 minus x. So once I took the derivative, now it looks like all the other problems did. So now we can find the first term pretty easily. That's just 1. We can find the r value. That's just x. So that's pretty simple. Or not 1, sorry, that was -1. Okay. So now I can go ahead and write down the power series that represents the derivative. So if I write that down, I'm going to say that the power series that represents the derivative would be from 0 to infinity of -1 times x to the n. All right? So if I want to take that and then figure out what power series would represent the original f of x and not the derivative, then I'm just going to say, well, if I integrate the left side, then I get from the derivative back to the original function. So then if I go ahead and integrate this side, then I'll be able to know what power series represents f of x. So to integrate, we're just going to add 1 to that exponent and divide by that exponent. So I've got -1 times x to the n plus 1, all divided by n plus 1. So I was being kind of clever to do that problem. Okay, so let's go ahead and do the examples that were on the back page, or the back side of that page. So it says, find a power series that represents 1 minus x squared, centered at 0. And then they're giving you some hints because this would be a hard problem to do without hints. So they said, what is the integral of 1 minus x squared? And then what is the radius of convergence? They want you to find that kind of after you're all done with the problem. So since they gave us that hint, we're going to go ahead and use that hint to do the problem. So I'm just going to kind of ignore everything else I was thinking and just say, all right, let me integrate 1 over 1 minus x squared and see what happens. So to do this integration, we do have to use u substitution. So I'm going to say the u is all the stuff inside the parentheses. And that makes du negative dx. And we don't have a negative hanging out on top, so I'm going to have to move that to the front. So I'm going to have the negative integral of 1 over u squared du, which is the same as the integral of u to the -2 du. So when I integrate that, I go ahead and I add 1 to the exponent, so I'm dividing by -1. And I can see that these two negatives would cancel. So I would actually end up with u to the -1, which is the same thing as 1 divided by u. All right. So that means that the integral is 1 over 1 minus x. Okay, so if I take this and I take the derivative of it, that's going to give me 1 over 1 minus x squared, right? Because if the integral of this gets me to this, then the derivative of this would get me back. Okay, so I'm going to think of it that way. All right, so now if I take this one and I go ahead and write a power series, a geometric power series for it, I can say n equals 0 to infinity. My first term is 1. My r value is x. and this is to the nth power, and that represents this. So if I want to know what power series would represent this, then I just have to take this part right here and do the derivative of it. So take the n, multiply it in the front, so n times x to the n minus 1. And I want to make sure that my first term, if I look here, my first term still needs to be 1. So I'm going to say this is from n equals 1 to infinity. And the reason for that is because if I plug a 1 in for n and a 1 in for n, that still gives me my first term of 1. All right. So this is my power series. What you'll notice is that if you compare these two, based on these, we have the absolute value of x is less than 1. Will help us find the radius of convergence. Over here, the absolute value of x is less than 1. Helps us find the radius of convergence. And so we're going to notice that the radius of convergence, whether we're talking about a derivative or an integral, it's going to stay the same. And we've referenced that before. And that's one of the reasons we can kind of go back and forth and do these difficult problems where maybe we're getting stuck and we're like, oh, let's just take the derivative instead, or let's integrate it instead to find our answer. So it has a radius of 1. That did not change. Okay, number 6, find a power series that represents ln 1 minus x centered at 0. And this is just a hint. This is exactly the same as warm-up number 4. So we are not going to do that again because we just did it. Okay, find the interval of convergence between these two. So if we look at this, we're going to have to do this interval of convergence and this interval of convergence and then kind of compare them. So here we're going to say the absolute value of negative x is less than 1. Here we're going to say the absolute value of x divided by 2 is less than 2. So if we were looking at this one over here, I would say, oh, this interval of convergence is from negative 1 to 1. And then over, not less than 2, sorry, less than 1, I was getting ahead of myself. To get the x alone, we're going to multiply the 2 over to the other side. And so we're going to say absolute value of x is less than 2, which makes the interval of convergence for that portion from negative 2 to 2. So if you're looking at the interval of convergence of the sum of these two different series, then you're going to have to go with the more conservative answer. So like negative 1.5 would make this one converge, but it wouldn't make that one converge. So we couldn't say it's an interval of convergence for the whole thing. It would not be within the interval for the whole thing. So the only part of the interval that's like redundant for the two problems is from negative 1 to 1. Negative 1 to 1 is included here and it's included there. So I think of it as the interval of convergence is the more conservative intervals of the two, or it's the one of the two that includes less numbers, or it's like the inside of the two. However you want to think of it, that would be the interval of convergence for the combination. Okay. Next, says find the sum of each series. So when we look at these series, we know that these are special polynomials that were written out to represent the equation of a curve that was not normally a polynomial. So it might be e to the x, it might be a rational function, it might be a sine curve or a cosine curve. So if we want to find the sum of the series, really the sum of the series is if this polynomial went forever. And if this polynomial went forever, then it was a perfect representation of that curve. So if we want to find the sum of the series, we just need to find the curve that it was trying to represent and then plug it into the curve instead. So if you look at this, think about this curve right here. I'm ignoring the pi's, I'm putting x's there instead. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. If you recognize that, that is the function f of x equals cos x. And this is the polynomial approximation for it. So if we were to take this polynomial approximation and we were to continue it forever, it would perfectly be represented by cos. So if I want to find the sum of the series, and it looks like they plugged in pi, then if I plug pi into cos, I can get the sum without working very hard. So cos of pi, if I think about my unit circle, pi is over here. And that point is -1 for x and 0 for y. And so cos of pi equals -1. It equals the x coordinate. So the sum of the series is -1. And you would find that if you continue doing more and more terms and adding them together, you would find they were getting closer and closer to -1. All right, we're going to do the same thing here. I'm going to rewrite this a little bit because I think this squared is in a weird spot. So, or not in a mathematically weird spot, but just maybe not making it as obvious for us to see how this one was working. Put those backwards. So when we looked at this function, we usually saw like an x here, an x there, an x there, an x there. So 1 plus x squared over 2 factorial, plus x to the third over 3 factorial, plus x to the fourth over 4 factorial. So this function, this polynomial is representing e to the x. This is the Maclaurin polynomial for e to the x. So that means if we want to find the sum, then we can just use the curve e to the x, and we are evaluating it at ln 4. So e to the ln 4. Now e's and ln's cancel each other out, and so this is just 4. All right. Let's go ahead and do the last one. So here, I can see an x there. So this one, if you guys notice, the 3 factorial, 5 factorial, 7 factorial, those all make sense. There's a 2 in the front. I'm going to go ahead and take that 2 out and kind of write what we have. So x minus x to the third over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. So it's kind of like they used the Maclaurin polynomial, but they had a 2 in the front, they distributed to it. So this Maclaurin polynomial represents sine of x, and then there was a 2 in front being distributed to that polynomial, so that means there was a 2 in the front of sine x. Okay. So now we're looking, and we know that the x had a pi 6 being plugged in. So I'm going to go ahead and say the function evaluated at pi 6 would be 2 times sine of pi 6. And I have to think about my unit circle. So pi 6 is down here, and it has an x value of √3 over 2 and a y value of 1/2. So this is 2 times the y coordinate 1/2. And so this is 1.